Hello there, my name is Gaya. I'm a PhD student at the Institute for AI at the University of Bremen. In this video, I'm going to walk you through a tutorial for developing a program on a simulated PR2 robot for executing simple mobile pick-and-place actions. To program our robot, we're going to use the CRAM framework, which is a toolbox for designing, implementing, and deploying software on autonomous robots, with a special emphasis on the mobile manipulation domain. So let's go to the CRAM website, which is cramsystem.org, and on the tutorials page there's a link to the Zero Prerequisites demo tutorial, and this is the one that we're going to go through together in this video. So the idea of the tutorial is to give you an intuition on the complexity of executing a mobile pick-and-place action on a robot. So you're going to learn what actions the robot needs to execute and in which order, and what should be the parameters of those actions. Basically, what knowledge does the robot need to have to successfully bring an arbitrary object from its environment from location A to some location B. We will also learn what can go wrong during execution and learn simple strategies for handling the failures. And for the people who are interested in the CRAM framework itself, you will learn what robot actions are already implemented in the framework, such that you can use them right away as building blocks for your own application. In this tutorial, we do not require any robotics or Linux background knowledge, so we try to keep it as simple as possible, such that the people who are new to this can hopefully also keep up. To run the tutorial, we will need a virtual machine. We are using the VirtualBox application for that. On Ubuntu, you can install it as a Debian package from the Ubuntu package repository. I have Ubuntu here, so I'm going to open a terminal by pressing Ctrl-Alt-T, and I'm going to input these two commands, my password, and the second command. And as you can see, I already have the newest version installed, so it goes really quickly for me. Okay, and on Ubuntu, on Windows or Mac OS, the VirtualBox is also available for free, and you can find the links on the tutorial page on how to download the VirtualBox there. Once you have the VirtualBox installed, you need to download the image for our virtual machine, which contains Ubuntu 16.04 and all the dependencies that we need to run our tutorial already installed and set up. So this virtual image is 10 gigabytes big, and if you don't already have it downloaded, then please do so and pause this video until your download is completed. Okay, but once you've got the virtual image downloaded, you'll need to fire up the VirtualBox and set up the virtual machine. I'm going to start the VirtualBox through a terminal, VirtualBox, and this is our VirtualBox. I'm going to click on New. It probably starts for you in the guided mode, so I'm going to click on Expert mode, and then we're going to name our virtual machine CRAM VM. The type of the operating system is Linux, and we have a 64-bit Ubuntu here. On this machine I have 8 gigabytes of RAM, so I'm going to allocate 4 of those for my virtual machine. If you have 16 gigabytes, I would suggest to allocate 8 for the VM, but anything between 4 gigabytes and 8 gigabytes should be sufficient. Okay, and we're going to create a virtual hard disk from a file. I'm going to go to the downloads where I downloaded the 10 gigabytes file just now and click create. Okay, as an optional step to make our VM a little bit faster, I'm going to allocate more than one processor core to it. So I'm going to go to Settings, System, and Processor, And here we can see I have 8 virtual CPU cores, so I'm going to allocate 4 of them for my VM. Anything up to half of the amount of the cores you have should more or less be fine, but 1 should also suffice. So anything between 1 and half of the cores that you have. Okay, so let's fire it up now. I'm going to full screen it. The user and the password in the virtual machine are already set up, and the user is CRAM and the password is also CRAM, but it logs in automatically. So, but if you accidentally log out because you were idle or so, then you can just enter the CRAM. Password is the same as the user and it will log you back in. Okay, so first of all, I'm going to full screen my virtual machine here, view full screen mode. And to go back, you can press Ctrl F and right Ctrl F back to full screen. And I'm going to open the tutorial page in the browser in my virtual machine here, so I can copy paste code from here into my IDE. The browser automatically opens on the tutorial page, and we're going to jump into the simple fetch and place part of the tutorial. To do our mobile pick and place, we need to have a bunch of processes running, be it on the real robot or in simulation. To start these processes, we are going to use a ROS launch file. ROS stands for Robot Operating System, which is a middleware that is commonly used by roboticists nowadays to develop, run, and distribute their software. So I'm going to open a new terminal by pressing Ctrl-Alt-T, or you can just click this tutorial button here, this terminal button here, and the terminal appears, and I'm going to copy the command, this one, into my terminal. To copy paste, I simply select the text in the browser and then press the middle click of my mouse in the terminal, or you can of course just right click copy and right click paste, or you can also Ctrl C in the browser and then Ctrl Shift V in the terminal. Ctrl Shift V for pasting in the terminal. Okay, so this launch file that we just started, it starts, for example, an inverse kinematic solver program that our robot will use. It also provides a 3D description of the environment that our robot will be acting in. It's a 3D representation of the kitchen that we have in our robotics lab here in Bremen. And it will run a bunch of other things that the robot will need. Okay, our development environment is going to be Emacs, which is one of the 2 main editors in Linux together with Vim, but we do not expect you to have any previous experience with Emacs in this tutorial. And the programming language we will use is Common Lisp, and again this tutorial does not expect you to have any prior knowledge of Lisp, or as I already mentioned, Linux or ROS, the robot operating system. So let's just start our IDE by executing the following command in a fresh terminal. To open a new terminal, I press here Ctrl-Shift-T to get a new tab, but you can also just click on the icon here and get a new terminal. So, and this is our command line of the Lisp programming language. We can do some simple operations here now. For example, we can type it has a German keyboard here, so I'm going to change it to English. And we can type 1 + 2, and we will get the answer 3. As you can see, Lisp has this prefix notation, so you need to put the operator first and then all the arguments follow. It's a bit awkward when you're not used to it, but yeah, one gets used to it quite quickly. So this command line right now can only execute Lisp operators. For example, the plus is like a common Lisp operator that's already defined here. And now we're going to load the robotics libraries provided by our tutorial in addition to the things that are already defined in the Lisp language. So for that, I'm going to copy this line into my Lisp command line. So we are loading the CRAM pick and place tutorial system into here, and it compiles the library source code. It takes a while, perhaps. Yeah, and now it's done. And next is this command, which switches into the namespace of the tutorial, such that we do not have to prefix all the functions from the tutorial library with the namespace of our package. So basically the CRAM pick and place tutorial is going to be our new namespace, and you see that the old namespace, which was CL user, which stands for Common Lisp User, switched to this pptut, which is the nickname of our CRAM pick and place tutorial package. Okay, and now we'll launch our simulation environment here by copying this. This is going to take a while. The virtual machine has a bit older, more stable version of the CRAM framework. The newest version doesn't take so long anymore, but we'll just have to wait for a couple of minutes here, 2-3 minutes. Okay, to copy paste things into Emacs, I either again select things in the browser and middle click in the Emacs, or you can Ctrl+C in the browser, but you cannot Ctrl+V in Emacs. For pasting, you press Ctrl+Y, which stands for yanking. The shortcuts in Emacs are the same as in the tutorial, in the terminal shortcuts. So basically in Bash, you can also type something in, and then I can go to the beginning of the line with Ctrl+A, the same as in Emacs. Then I can kill the line by Ctrl+K. Then I can type something else and Ctrl+Y to yank the basically what I just copied back. So the Emacs shortcuts are the same as Bash shortcuts, and they are much older than the Windows Ctrl+C, Ctrl+V shortcuts actually, that most people are used to. And although the Emacs shortcuts seem unusual to people, from the history perspective, it's actually the Windows shortcuts that are unusual. But yeah, we have a cheat sheet for Emacs on the CRAM website and some useful links to teach you more about Emacs if you're not already familiar with it. Okay, let's see how it's doing. Still compiling and starting the node. And now it's done. So here shows up our simulator. You can move the camera by holding the right mouse button and dragging around, or you can change the angle of the camera by dragging the left mouse button, and you can zoom in and out with scrolling. Okay, and this is our PR2 robot in our lab kitchen. Okay, so let's try to move him around in this environment. So currently the coordinate of the PR2 in the environment is 0, 0. And the x-axis points forward for the robot, as shown on this picture. So the red axis is the x, points forward, and the green axis is the y, points left, and the blue one is the z, points up. So let's define a new pose in this environment for the robot to go to, for example this one, which will be in x 0, in y 1, and in z 0. So 0, 1, 0. The squares here are 1 meter big. And the rotation will be identity, so he will keep his orientation. We're going to use the function MakePose for this. So let's just copy that one here. And the first argument of MakePose is the coordinate frame as a string. So the name of the coordinate frame that the coordinates are defined in. We are using map which is the standard name for the global coordinate frame in robotics, or at least in the ROS community. And then the pose is the nested list, where the first part has the x, y, and z coordinates, and the second part is the orientation of the robot, represented as a quaternion. So the quaternion is one of the most convenient representations that one can use to represent rotations in space. And this is the representation that is also used in the ROS community. This is why we are using it here as well. So we're going to use the identity quaternion, which is 0, 0, 0, 1. The quote here at the beginning means that we're creating a list data structure that is not a function, so it shouldn't be evaluated. So basically, this is just a data structure. Okay, to evaluate, let's click enter and see what we get. The result is highlighted in red. When we right-click, we can right-click on any of the results that we get from execution, and we can inspect it. And then we see here that this coordinate is an object of class post-stamped, and it has a bunch of member variables here. So the frame ID, the orientation, the origin, and the timestamp. Okay, let's press Q to exit this window. And yeah, let's command the robot to move to this location. For that, we're going to use this code. Okay. To select a region between two brackets, I press Ctrl-Alt space, and then to fix the indentation, I press Ctrl-Alt backslash. Or you can select and then say Alt-X, indent, it writes here indent region, tab autocompletes, enter, and then we indent the region. Okay, so what is going on here in this text, in this code? It starts with simulated robot, because there also exists with real robot. If you want to execute the same code on the real robot, you can just switch this to with real robot, and then without changing anything in the code, it will switch automatically. So this is one of the ideas of the CRAM framework, that it allows you to switch between execution on different robots or in the simulation and the real world without having to change anything in your code. Okay, and the next thing is this let block, which is a block for defining local variables. So it's like in math, we let us have a variable navigation goal, and let this navigation goal be this expression. And this is what we just typed in here, so this coordinate. We defined the local variable navigation goal here, and the name can be anything. The question mark doesn't actually have to be here. It is necessary for what comes next. So you can name your local variables anything you want. And what comes next is this perform call. So it's the perform operator, which gets as input an action description. That's the only argument of this operator. And it performs it on the robot. So let's break this down a bit for a second. I'm going to remove the with simulated robot part, only leave the let block, remove the perform, and only leave the action description. And press enter. So what do we get is an action description data structure. And if I right click inspect, I see that it's an object of class action designator, which has a bunch of member variables. But basically what happens is that this expression gets creates a new action description object of this class, and the key value pairs here, they stay the same unless they have a question mark in front of them. If these keywords have a question mark in front, then they get replaced by the value of the variable. Okay, so the variables inside of this description have a question mark suffix and then prefix, and then they get replaced by the value of the variable. All right, so we get this action description. Now let's just perform it on the robot. We say perform this action description, and we always need to say where we perform it, on the simulated robot or on the real robot. So with simulated robot, perform this action. And we observe that our robot moved from here to here. Now let's change it back to 0, 0, 0. To go back up in my history, I press Control up. I can go Control up or Control down. And then I can find what I input before. So let's give it again 0, 0, 0, and then see that the robot moves back to 0, 0, 0. Okay, so this is how we command the robot to move around in the environment, by performing an action of type going to some target location, where the pose we define by using this MakePose function. And now let's define a new pose near this table, because we will try to grasp some objects from this table. So if this is the x-axis pointing forward, then to go back, we would need to go in the negative direction of x. So let's say 1.5 meters in x. Let me just quickly visualize the origin of our coordinate frame by calling visualize coordinates function. And now I'm going to make a new pose in map, which is 0, 0, 0. Oh. And I can also say how big I want my coordinate frame to be. Okay, so here is our coordinate frame. So to stand somewhere here for the robot, we need to go minus 1.5 meters in x. And we need to probably come a little bit closer to the table, so we go in this direction, which is minus y. So let's say minus 15 centimeters in y, and the robot always stands on the floor, so the z will be 0. Let's look here. Basically, here is pose defined for which is a pose near the table. Let's just copy that one. So it doesn't have 1.5 but 1.447 and minus 0.15 and 0, as we said, and the orientation is written as a quaternion such that the robot faces the table here. So let's see, we make a pose in the map coordinate frame where this is x, y, and z, and this is the orientation. These d0s that you see after the numbers simply mean that the number is in the double float precision, so a double precision float. And if we don't have a d0, it will be a single precision float, which actually doesn't matter so much for us at this moment. So you can really just ignore it, or understand that if you have a d0, it means it's a double precision, and if you don't have a d0, then it's a single precision. And this def parameter is a Lisp command for defining global variables. So we're defining a global variable called basePose near table, and we store in that variable this coordinate. The stars, the stars asterisks before and after the name of this global variable are there just because it's a convention in Lisp to name global variables with these stars. You don't have to do it, but it's nice to do it, to stick to the convention. Okay, we press enter. We get this basePose near table as a variable. If I right click on it, I can see that it is a global variable bound to this value that we just gave it. Okay, and if I want to just see what's inside the global variable, I can also just write its name and press enter, and then I will get the value of this variable. Okay, so let's command the robot to go to the table. With simulated robot, we say our navigation goal is not this pose anymore, but the basePose near table, and then we just say perform an action type going. the order of, if you say perform first and then the let block, or the let block first or perform after, it doesn't matter. So, I pressed enter, and then I observed that the robot moved to this pose. Let's send him back to 0 to 0. And now, instead of 0 to 0, I just say base pose near table, tab autocomplete. Then I execute the same thing, and then we go to the table. Okay. So now that we're at the table, let's spawn an object on this table such that we can grasp it. For spawning object, we're going to use spawn object function, which gets as an argument the coordinates of the object. So we're going to spawn the object at minus 1.6 in x, so 1.6 minus 0.9 in y, which is somewhere around here, and then 0.82 in z, so it will go up on the table, so it will be somewhere around here. And the orientation is again identity orientation. I press enter, and I see that a bottle appears, a red bottle. We can spawn other types of objects, not just bottles. To find out what objects to spawn, what objects are available, we can call list available objects function. And then we see there is a tray, a spoon, a cup, a milk, a shoe, and this bottle, which is the default. So for example, let's spawn a Weißwurst object, this guy, type Weißwurst. So you can see when you click somewhere in the function below here, so we can see all the arguments of the function here. This is the spawn pose, the first argument, and then come optional arguments, which is first the object type. The default value is bottle, that's why we get the bottle per default spawned, and now we're going to call it with Weißwurst, this one. Then comes the object name, which per default is bottle1. We're going to call our object Wurst1, and then the color is per default it's a red color, red, green, blue. And now we're going to spawn a green one, red, green, blue. So green Weißwurst, which is this Bavarian sausage, and we see the object appears right here. Okay, and to grasp an object in the environment, the first thing that we need to do is to perceive this object in order to know the exact coordinates of the object in space. And there are a number of things that you need to consider before commanding the robot to perceive something. First, obviously, the robot has to be standing at the location from where the object can be seen. So not too far away, and there shouldn't be any occluding objects in the way. So he cannot be standing, for example, behind this wall. The camera has to be at the appropriate height. And in human environments, it's the best to have the robot camera at the human eye level, usually. So the camera here in the robot is going to be located somewhere here. And our robot has a torso joint which can go up and down. So we will command our robot to go up such that his camera is at the human eye level. And finally, the arms of the robot have to be out of the way of the camera. Okay, so to do that, let's send the appropriate commands to the robot, and that's happening here. So what is going on here? We have the navigation goal stored in the local variable, again, this base pose near table, which is this coordinate that we defined. And then we are performing a going action to go to this pose. I mean, right now the robot is already standing here, but we are going to reuse this code later. So we're going to command the robot to come here in any case. And then we are going to command the robot to move the torso up to the maximum joint angle. And then we're going to park the arms to make sure that the arms are out of the way. And the par operator here is a common Lisp operator it's a operator not in common Lisp but defined in our library, in our robotics library, which allows you to execute multiple things in parallel threads at the same time. So it takes care of creating the new threads and then destroying the threads, and you don't have to call the operating system API yourself. So it takes care of these things under the hood for you. And you probably also noticed that here the moving torso is a motion. Before we were only executing actions of type going, and now this is a motion of type moving torso. Basically both actions and motions are very similar, only motions are more low level conceptually in the CRAM framework. But in this tutorial you really don't need to understand the difference between the two, just know that you can tell the robot to execute either an action or a motion by calling the perform operator. So I'm going to press enter and see what happens. The robot parks his arms, goes with the torso up, and yeah, stays at this location. Let's execute the same thing with maybe a different torso angle, 0.0, and you see that the robot can get very small. And from this location he might not be able to perceive objects that are high, for example on the fridge there. And now let's command it back to go to 0.3, and now he's ready to perceive. Now the last thing before perceiving is directing the camera of the robot towards the object. So we need to move the robot's neck, and this is done via the looking action. As you can see right now the robot is just looking forward, and if I put the camera somewhere where his eyes would be, I don't really see the object. I maybe see a tiny part of it, but I don't really see it. So I need to direct the camera down to be able to perceive the object. But first we need to define where on the table are we going to look at. So where are we going to direct our gaze? And this should be somewhere near the location where we expect to find the object. And you notice that this is another piece of knowledge that the robot needs to have for mobile pick and place. In addition to know where to stand to perceive an object on this table, he also needs to know where to direct his gaze. So let's copy the pose on the table that is defined in the tutorial. And that is this downward looking coordinate. And you see that the coordinate frame is not map anymore, but it's base footprint. Base footprint is the coordinate that is in the base of the robot. So it's the coordinate frame right here. I'm going to visualize it for you by calling visualize coordinate, and that will be the pose where we're standing right now, base pose near table with some bigger marker. So this is it. The base footprint coordinate frame here is this coordinate frame. So x points in this direction, y in this direction, and z up. In that case 0.6 in x will be somewhere a half a meter about here, and then 0.0676 is just a little couple of centimeters to the left, and then 75 is up. So he's going to try to look more or less in front of him, down. So let's command the robot then to move his neck to look at that location. Copy, yank. So we perform an action of type looking at a target, which is a location with some pose. The looking direction variable is then assigned to this downward look coordinate variable value. So we're going to look at this location with respect to the robot base frame. And when I press enter, I observe that he looked down now. And now we're finally ready to perceive. For that we are going to call the detecting action. So we perform an action type detecting object and object type bottle. And what we get is a description of the object as an object description data structure. So we get a type is bottle, the name is bottle1, and we have some pose which is defined in the robot coordinate frame. So now we know exactly where the robot is, where the object is with respect to the robot coordinate frame. Let's store this result in a variable. We're going to define a global variable called perceived bottle, which is currently nil. So if I say perceived bottle, it's going to be nil. And to set the value of this variable, I'm going to use the setF operator. So instead of saying perceived bottle equals something, in Lisp you say setF, perceived bottle, and then the value. And I can either copy this part here, and now I'm going to use the star that can be used in the command line of Lisp, which just says, so 1 star is the previous result, what we got from the command line, and 3 stars, for example, is you go 3 up, 1, 2, 3, so it will be the nil, and 4 stars don't exist, so there's only 1, 2, or 3 stars, and 2 would be 1, 2, so this one. Okay, let's see what we have in the perceived bottle variable now. We have our object inside there. So we're finally ready to pick it up. For that we need to perform a picking up action. So I'm going to copy this. So we perform an action of type picking up with the right arm with the left side grasp of the object, which is this variable, and this variable is bound to this variable, and that is the object that we just perceived. So, and then afterwards we park the arms. Let's see what happens. And you can see he reaches for the object, closes his gripper, and lifts the object. And finally, now let's place the object at another table, for example at this kitchen island table. For that we need to define a pose where to place the object and a pose where the robot should stand in order to be able to reach that location. So those would be these two poses. So we have a final object destination coordinate in the map frame, which is minus 0.82. Let's see, if the x points forward, then minus 0.8 is going to be in this direction, so somewhere here, and 2 is the y points to the left, so 2 meters to the left is going to be here, and then it's going to be 0.9, so on the table. So somewhere here we're going to try to place this object, and our base location to be able to place it is going to be minus 0.15, so a little bit here, and then again 2. So the robot is going to be standing here, and this is the orientation such that he is facing the table. Okay, let's define these two global variables, and now we perform the placing action, which is here. So what happens here? We have a navigation goal, and we perform an action of type going to this base pose near counter. So we navigate, then we perform an action of type placing with the right arm. The object is in our right arm, the right hand. The object itself is the perceived bottle, which is bound to the perceived bottle variable that we define here. And the target of the placing action is a location on this table, so the drop pose, which is bound to this final object destination variable. And when we're done, we're going to park our right arm. Okay, and you can observe that he placed the object and parked his arms. Great, we have just successfully picked and placed the bottle object. The Lisp command line is good for rapid prototyping. So you can quickly type something in here, tweak some values, and right away observe the result of the actions. But once you more or less know what to do, it's nice to store your progress in a file. So we're going to now define a function that does this full pick and place process for us and save it in a file. For that, we already prepared a nearly empty file for you. In Emacs, you press Ctrl X, Ctrl F to open a file, and the path to the file is here. So it's workspace, source, CRAM tutorial. I'm going to type it here, tab, source, CRAM, source, CRAM tutorials, CRAM pick and place tutorial, source, and here there is this pick and place file. With tab you can always autocomplete. I'm going to press enter, and there it is, our nearly empty file. The only thing that it contains right now is this in package operator, which ensures that everything that we write below is going to be belong to the tutorial namespace. Now we copy paste the contents, this code, into our file, and we press Ctrl X, Ctrl S to save the file. Or you can also press this button here. So you can see when I change something, these stars appear here down, and when I save, they disappear. Okay, so what is in this code? We define a new function called moveBottle, which has one input argument called bottle spawn pose. Then we spawn this object. Then we have we perform a navigation action to go to the base pose near table, which was a pose here. We move the torso up, we park the arms, then we look down. If you remember, the downward look coordinates are these ones that are defined in the base frame, in the robot frame. And then we perceive the object of type bottle. We store the result in the perceived bottle local variable. Then we perform a picking up action on this variable. Then we go to the base pose near counter, which is here. And then we perform the placing action with this object at the target location drop pose, which is final object destination here. So basically everything that we just did is executed here at once within this moveBottle function. So I'm going to compile this file by pressing Ctrl C, Ctrl K, and you can see it says compilation finished. And then I can, so this compiles the whole file, and I can also compile parts of the file by just pressing Ctrl C, Ctrl C. And it highlights it with yellow. And now this function is defined, and I can also use it in my command line. So now we're going to change back to the buffer of the command line by pressing Ctrl X, B. And yeah, keep in mind it's not Ctrl X, Ctrl B, it's Ctrl X and just B. And then it says here slime REPL, and I'm just gonna press enter, and I'm back in the REPL. Okay, so then let's just call this function. As you remember, the argument of moveBottle is the spawn pose, and we're going to spawn the object at the original pose here on the table, so minus 1.6, minus 0.9. So here we're going to spawn the bottle, and we're going to try to pick and place it. There we go, he moves the head. Whoa. We're going to just retry, and then it works. So let's do this again. Okay, so we can successfully pick and place the object like this. All right. Now the move bottle function is great. It can transport the bottle from the table to the island area, but where do all these poses come from in the function? So how do I know where to stand? How do I know where to look, where to place the object, and so on? So how did we know that we should grasp the object also with the right arm and not with the left arm? And the explanation is that we knew exactly where the object is going to be in the environment, so we could define the poses manually such that they fit. But what if the object is at a different location? In the real world, we cannot assume that the objects are always at the same location. So let's assume that it's still on the table, but a bit further to the right now. Will our plan move bottle action, move bottle function still work? So let's try this out. Let's call it with a different, Control X B, enter. Let's call it with a different coordinate. So previously we spawned the object at -1.6, -0.9. And now we're going to use the same pose, more or less, only 40 centimeters more to the right here. And we see that the robot is trying to perform its actions, but we get this error, could not find the object of type bottle. And we end up in the debugger. We get here a condition of type perception object not found. So basically, the robot is now looking down, but the object is not in the field of view anymore, so he cannot see it. Basically, the view is something like this for the robot. So let's exit the debugger by pressing Q here, Q, and try to fix this problem. So for that, we're going to write a simple failure handling strategy. We will define a bunch of additional poses for the robot to direct its camera at on the table. For example, now he's looking here. Let's define another one on the left and another one on the right. And we will iterate over these poses until the robot finds the object. So we used to have the downward look coordinate here. I'm going to Control X B back to the pick and place file. We have this downward look coordinate variable, and now we're going to add two more of those, one on the left and one mirrored on the right. To add these to the file, let's copy them here from here. Left downward look coordinate and right downward look coordinate. You can see they are pretty much the same as this one, only in Y now we have 0.76 and -0.76. So right now he's looking here, which is 0.076, and now we're going to add another one here, 70 centimeters to the left and 70 centimeters to the right. I'm going to Control CC, compile this new global variables. And now we're going to define a find object function, which will do this failure handling. It will iterate over the different looking poses until the object is found. So I'm going to copy it right here. And I'm going to Control X, Control S to save the file, and Control C, Control K to compile the file. So what does this function do? We have a list of look directions, possible look directions, a list of 3 members, 3 coordinates in here. This back quote simply says that I'm going to create a list where these guys should be replaced with their values. So let's go back to the REPL, REPL tab, and if I press enter, I just see a list of these 3 coordinates that we just defined. And if I had a simple quote instead of back quote, I cannot use commas here. So it would look like this, and then it would just be the names of these variables in the list. And I don't want to have names, I want to have the values instead. So that's why we're using the back quote here. Okay, and the looking direction variable is going to be the first from this list. So he's going to try to look in front of him first. Then we are performing the looking action, and then this interesting handle failure operator comes in, which says try to perform a detecting action, so try to perceive the object. If it works out, then we are done. But if it doesn't work out and you get a perception object not found failure, then we will do a failure handling strategy. What is our failure handling strategy? We say as long as the possible look directions list is not empty, we're going to first look forward, then we're going to assign to the looking direction the first of this list. So currently the looking direction is the first of this list, so the downward look coordinate, and the possible look directions have the rest, so these two. And in the next iteration, if a failure happens, the look direction will be this one, and the possible look directions will be a list of just this one value. And then we look down again and retry. So we retry to execute this piece of code here again. So we try to detect. If we find our object at this point, when we looked to the left, then we're good and it's over. And if not, then we make another iteration. So again, the looking direction is going to be now the first of the possible directions, which is this one. So the next one for the looking direction will be the right looking direction. And the possible look directions is going to be the rest of it, which is going to be an empty list. And we're going to look to the right, retry again. If we find our bottle, which we hopefully will, because the bottle is on the right, then we're good. And if the bottle isn't even there, then we're going to retry again. We're going to get the failure again. And then this when will say the possible look directions is already empty. So this part is not going to happen. And we're going to just look forward and propagate the object nowhere to be found failure up to the high level. Okay, so I'm going to compile this. Going to go back to the REPL, to my SBCL REPL, and let's try to execute this function. I'm going to say find object, and the argument of find object was object type. So I'm going to just say bottle, and we always need to not forget to say with simulated robot here, because you can see in the move bottle we already had with simulated robot inside, and here in the find object we don't, so we should specify it. And yeah, let's see what happens. The robot looks to the left, doesn't find the object, looks to the right, finds the object. You can see it here as well. He could not find when he looked down, then perception error happened, turns the head, perceives again, and then perceives again on the right side and finds the object. Now let's spawn the object of the bottle object somewhere else. MakePose, for example, at 0, 0, 0. So here, and see what happens if we now try to find the object or the bottle. So the robot looks down, cannot find the object, looks to the left. Oh, and when he looks to the left, he apparently ends up with the bottle in his field of view somehow, here, there. But let's try to find an object that really doesn't exist in the world here. For example, a cube. A cube doesn't exist, so he looks down, he looks to the left, he looks to the right. The cube doesn't exist. He looks forward, and we get an object nowhere to be found failure, and we end up in the debugger. Okay, press Q to exit. So, and yeah, and with this we successfully handled a failure with a simple failure handling strategy. And this concludes our video, but it does not conclude the tutorial actually. There is more content on the tutorial web page on the website, There are other failures that are considered here, and more elaborate failure handling strategies are developed. And at the bottom here, there are also exercises that you can try to solve on your own. And they also have the difficulty level specified here. And I also give you a little secret. If you click on this little dot here, you will find the solutions to the exercises. So yeah, I hope you enjoyed this tutorial. I hope you learned a little bit something for yourself from it. If you're interested in learning more about the CRAM framework, we have a lot more tutorials that you can try. And here at the top of the page is the link. And there's also instructions on how to install the system on natively outside of the virtual machine, so natively on the Linux operating system. And with that, I thank you very much for your attention. Goodbye.